Hello everybody, welcome to Chapter 7 lecture. Today we're going to be examining probability in samples and the distribution of sample means. First, let's take a second and look at where we've been. So in Chapter 6, we were able to take a particular raw x-score and find a z-score. And we were able to take that z-score and then find the probability of selecting that z-score or more. So we were able to look at the probability under the curve. And this is, really interesting for a very particular problem we want to solve, a very particular question we want to look at. However, most of the time we are interested in looking at samples that are larger than one. So let's take a look at what we were doing in Chapter 6. In Chapter 6, we had a sample size of 1. And so we randomly, let's just say, we wanted to select somebody out. We wanted to ask, what's the probability of selecting that individual? Or selecting that individual or greater, perhaps. So we randomly select 21. And the question is, how representative is that individual score for the population? And we'd go and we'd find a z-score like we did in Chapter 6, and we could find the probability of getting 21. And here's the problem. The problem is we rarely are looking at an individual score. What we're more interested in is samples. Like I mentioned in previous lectures, this is where we're going to start moving away from looking at individual scores and distribution to looking at sample means. So let's take a look at a sample mean. So instead of looking at one score, let's look at 3 scores. As you can see right here in notation, we have n equals 3. So this is a sample 3 we're looking at. And that sample mean is 23. Now compared to 21, 23 is a much more representative number for this population. It's much closer to the mean of 27, which we have here. This is our population mean, our population standard deviation. It's much closer to our mean, but it's not perfect. In fact, we can see that if we take all sorts of samples of 3 from this population, there are many possible means available. So we could randomly select somebody. For example, here we have one that this is lower than the mean. This is much higher than the mean. And this one's close to the mean. This is probably the most representative of the 3 we're looking at here. So each one of these samples are being pulled. And the question we could ask ourselves is, what is the probability of us selecting this? Now, what we call this difference between the population parameter, in this case 27, and our sample statistics, we call this sampling error. This is just the natural discrepancy we would expect to find when we are taking a subset of scores from a population, such as this one. Now, the problem with this, we're getting all these sorts of means, is that samples are supposed to be representative of the population. We want to make inferences based on these samples. So one of the questions we can ask ourselves is, how are we going to do this? Well, fortunately for us, this distribution of sample means, so if we looked at all possible sample means, we can come up with a distribution of sample means. So all the possible sample means that are possible given our population, given a certain sample size. So this concept of distribution of sample means is what we're going to be looking at today. So this is just the means of all the possible random samples of a particular size taken from the population. So, for example, previously we had looked at what's the probability, or we could take all the possible sample sizes of 3, because remember now we're doing sampling with replacement. So let's just look. So we could look at these 3, we could look at these 3, we could look at these 3 individuals. And we'd find all the possible samples. Now, as you can see, this could get really complicated really fast, but we're going to do an example here in a second that may show this. And like any distribution, we can describe that distribution in terms of its shape, central tendency, and its spread, or its variability. So first, let's look at our example. Now, I made a far more simple example for us to look at. This is also a version of this is also in your book. And let's say we have a population of just 3 scores to keep things very simple for us. So 3, 4, and 5. Now we know, looking at this, that the mean for this is 4, and the standard deviation is 0.816. And so if we're going to find the distribution of sample means, we need to find all possible combinations of n equals 2. So we're going to take a sample size of 2, and we are going to find the mean for it. So the first step is we go through and find all the possible combinations here. So, for example, just to very briefly go through it, so we could randomly select 3 and 4, 3 and 5, or 3 and 3, because remember we're sampling with replacement. So these are all the possible combinations that we could have, and so you can go through and see this. And this will actually be on your homework. Will be an example similar to this you'll have to go through. And now that we've done that, remember, this is all the possible samples in the population, so let's get all the means. So we quickly calculate the mean. So 3 plus 4 is 12, divided by 2 is going to give us 3.5. Oh, sorry about that. No, reverse that. So 3 plus 4 is 7, divide that by 2 is going to give us 3.5. I was multiplying when I should have been adding. So we have our means. Now this distribution of sample means, it doesn't make a lot of sense to look at it right now, but let's take another look at it. Now notice that if we add these sample means up, it's going to give us 36. If we take 36, we divide that by the total number of samples in this population that are possible, so 9, we are going to get 4. So that's going to tell us one thing about our population. If you notice that our population parameter and the mean of all possible means, or the distribution of sample means, is exactly the same. And this should make sense to us, because on average, we like to say we're average. We're more likely to select means that are closer to the center of our distribution. And so we are going to find that the population mean that we're drawing from is going to be identical to what we call the expected value of m. So let's take a look at the histogram for this distribution of sample means. So if you look at this distribution, there's a couple things that you'll notice about it. Now, as we know, the mean for this distribution is 4, because it's exactly similar to our population mean. And also notice that it's normally distributed. So on average, we're going to find the exact same proportion on either side of the mean. Now this is just an example, but this is an example that really will carry through to what we'll find later on in this lecture. But the basics we have here is that we have this distribution. And now we have this distribution, we can ask questions. Now, the first thing we need to know about this distribution is we need to be able to describe it. Now, as we talked about previously, there are many ways we can describe a distribution. We have a mean, or a central tendency, shape, and variability. The first thing we need to, in order to understand what this distribution of sample means shape is like, or how it looks like, is we need to look at what's called the central limit theorem. So the central limit theorem tells us for any population, so regardless of anything, the distribution of sample means with a given sample size will, and these are important characteristics, so any distribution of sample means will approach normal as sample size increases. We'll get more specific on that in a second. We'll have a mean identical to the population, so we've already kind of seen that in our example. And we'll have a standard deviation, so this is our spread of the population standard deviation over the square root of our sample size. And we'll dive into that more. First, let's look at our shape. This is probably the easiest one for us to look at. So we have this shape. And as we said, as sample size increases, it's assumed to be normal. Now, let's be a little more specific about that. There are two situations in which the distribution of sample means will be normal. The first one is kind of obvious. If the population that it comes from is normal, it will be normal. So if we're looking at something like height, which is normally distributed in the population, if we took a sample of 5, and we took all the possible samples of 5 in the population, we would have a normal distribution. The second situation in which a sample, the distribution of sample means will be normal, is if the sample is very large. So even if we have a skewed data, and we take random samples of 30 or more, and we took random samples of 30 throughout the entire population, it will form a normal distribution. So for example, if we were looking at something that is skewed, like test scores tend to be negatively skewed. We have more scores at the high end than at the low end, fortunately. So, if let's just say, for example, we had a lot more students. Let's say there was 10 sections. We had lots of students we could sample from this population. If I took all the random samples of 30 from that population, that will form a normal curve around the mean. So these are the two important things to consider, and I can guarantee you there's probably going to be questions on the test about this. A question would be very simple to ask. Maybe this is a question that you can stop and ask yourself real quick to answer it, even though we kind of just discussed it. When is the distribution of sample means normal? And there's two times when we'll know it's normal. If A, the normal, and or if the sample size is large. If we have that, we'll have a normal population. Now let's take a step back and think about that for a second. As we learned in Chapter 6, when we are looking at a z-score, and we're computing z-scores for a distribution, be it a distribution of raw scores or distribution of sample means, we know that what we need is that we need to have a normal distribution. If we're going to find a z-score for anything, we need to have a normal distribution. Now, because of the particular characteristics of the distribution of sample means, if the population it's coming from is normal, or if the sample size is larger than 30, we can assume that that distribution of sample means is going to be normal. And that's going to become important later on when we want to look at probability. But first, let's take a look at another aspect of shape, or another aspect of describing this distribution in terms of sample means or in terms of central tendency. But before we move on, there's one thing I do want to kind of bring home to us, because we've kind of been moving forward really fast. Let's take a second back, and what have we been doing in the past? Now, before, when we've been talking about this distribution, normal distribution, we've been talking about X scores. So individual scores within a population. Now, I want to remind you what we're looking at here is we're not looking at X's. We're looking at the sample means of all the possible sample means within this population with a given sample size. And so why it's the same distribution, a lot of things are the same. Conceptually, it's a little bit different here. And so as we move forward, if you find yourself drifting back to Chapter 6, remember here what we're looking at is sample means. And because of that, this distribution is going to be different from the population in some ways that it came from. But one way it will not differ is in terms of its central tendency. And this should make sense. So in the original population, we have a mean of, let's say we have 100, because that's what we've been working with. So IQ scores have a mean of 100. Now, IQ scores, of course, are normally distributed. So it doesn't matter what sample size we have. The distribution of sample means is also going to be normally distributed. And let's say, of course, here we also have a standard deviation of 15, but we're not going to worry about that right now. On average, we are expecting, when we're randomly selecting individuals from the sample, we are going to be more likely to select individuals towards the center. Remember, when we were talking about probability, what's the probability that we're going to be selecting an individual that is within one standard deviation from the mean? Now, of course, you go to your unit normal table, figure that out, but remember, it's about 68%, roughly. So we have a 68% chance of selecting somebody that is within one standard deviation of the mean. So over half the time, we're likely to select somebody that is actually close to the mean. additionally, because of that, we are going to have a lot of means that are closer to the mean, because they're going to be very similar to the mean. And so we expect that these means would fall here, right in the center. Now, we would expect outliers, just like we expect outliers in raw scores. Well, we'll have people for like me, so we look at height, right? So I'm really tall, so I'm going to be an outlier way out here. And we'd expect to find, if we took a sample size of 2 or 3, that we would find, you would randomly select 3 people that are really tall, or in this case, 3 people that are really intelligent, that have high IQs, or 3 people who have low IQs. So that's still possible. Now, how probable is it? Now, that is another question. Now, so this is something we have to remember. An important thing to remember is that our expected value of m, so we talked about that a little bit ago, it will always be equal to our population mean. So, again, this is another excellent question for a quiz or for the homework, is asking that very conceptual question. If I give you an original population mean, and I ask you what the distribution of sample means, you should be able to tell me what that is. So in this case, remember, it's your expected value of m is always equal to our population mean. All right. Now, let's look at another law. So we looked at the central limit theorem. There's another law that also helps us to understand the spread of our scores. And that is called the law of large numbers. The law of large numbers, so you can find this in page 182 of your book, basically says the larger the sample size, so the larger the sample that we pull, let us move forward here, the larger the sample that we pull from the population, the more probable that the sample mean is going to be closer to the population mean. So let's think about that for a second. The larger the sample size, the more probable that the sample mean is closer to the population mean. So for a second, you can mistake thinking, okay, so we know from central tendency that the population mean and the expected value of m is going to be exactly the same. But why would we expect to find that the larger the sample size, why would it be more probable that the sample means that we find from those samples will be closer to the population mean? Well, so let's look at this example. So let's go back to our age example. So we're talking about spread. Now, we're just going to eyeball this here, but let's ask us a question. What is the probability that we are going to select somebody who is the age of 50 from this distribution, right? So we have one individual who is 50 in this distribution, and so if we're just going to select a sample size of 1, if we're going to select a sample size of 1, what's the probability? Now, we could add it up, and I don't know. I believe it's... I can't off the top of my head. I don't know the number here. But we could do the probability. What's the 1 out of the total number of outcomes? We can find the probability. Or we could do the z-table if it's normally distributed. We could figure out that way. But I'm just going to ask you a simple question. Is it probable, or is it possible? Is it possible if we take a sample of 1 here, we'll get a mean of 50? And the answer is yes. Since we're only taking a sample size of 1, it is possible that we'll select somebody who is 50 years old. Now, let's take the same population, but let's have a sample size of 2. So here's our sample of 2. Now, I found the 2 oldest individuals in this sample, somebody who's 50 and 45. So this represents the most extremely high score, or this is the oldest individuals within our data set that we'd find, the outliers, the extreme scores. And we'll use it as a sample mean. So we can think of this as about the highest, is the upper end of sample means that we could expect to find. So if we do the math here, we got 45. So if we take 45, right, plus 50, will give us 95. Excuse my poor handwriting here. Find the mean of that, right? So that's over 2. So for this sample, we'll have a mean of 47.5. Again, you have to excuse my poor handwriting here. So the highest possible mean that we could possibly have here is 47.5. Why is that? Could we, so I go back to our original question, could we get a sample mean here that is equal to 50? And the answer is no. That's because the larger the sample size, the more likely we are going to be able to offset outliers. So in this case, we offset the outlier, even though I used the 2 highest scores within this population, it still brought it closer to the mean than if we just had a sample size of 1. Let's take this a step further. For example, let's say that we had, instead of a sample size of 2, we had a sample size of 3. So let's include into this sample 22. Right? Now remember, the mean of this distribution was 27, so this is slightly below the mean, but probably still within what we'd expect. So for this distribution, of a sample size of 3, we'd get a total, if we added them all up, we get a total of 117. So if we added 45 plus 50 plus 22, divide that by 3, what we'd get is 39. That would be our mean of that sample. And again, even if I used the next highest, so even if I was trying to add the most extreme scores to this population, which would be 40, right? Our mean would still be closer to our population. And that's important. First, it's important for us to realize that our probabilities are changing. Because the spread, the distribution that's possible, is now shrinking. So let's look at how we're going to measure this. We're going to measure this using what's called the standard error, or the estimated standard error. You can find this on page 182 in your book. So our estimated standard error tells us is basically what we consider the standard deviation from this distribution of sample. So in our previous, in chapter 6, we had a standard deviation for our raw scores. And just like that, our standard error is the standard deviation for this new distribution of sample means that we created. So let's look at the definition. As you can see here, the definition is nearly identical to that of what a standard deviation is. So the average distance, a sample mean, is expected to be from the population. So the important thing we have to look here is sample mean. We're not looking at an individual score. So the definition for standard deviation is the average distance a score is from the mean. So that's an important thing to remember here. So let's take a peek at what's possible with standard error. So let's take the smallest possible sample. So we've been talking about this n of 1, right? So if I just took all the possible sample sizes of 1, now if I did that, it would look identical to our raw score mean, because that is essentially a sample size of 1. We've taken one individual score, so those are all the possible means, per se, that's possible. And if we do that, our standard error, or the estimated distance we'd expect around the mean for our distribution samples, would be identical to our population. This is because nothing has changed. We're only looking at sample sizes of 1. So we can look at standard deviation of our population mean as our base rate. Our estimated standard error will never be greater than that. Okay? But let's see what happens when we increase our sample size. As we increase our sample size, so in this case we're using a sample size of 30. We start with a population of 15, standard deviation of 15 with a mean of 100. Notice our means aren't changing here. However, the expected distance we would expect to find a sample mean shrinks. Why is this? This goes back to the law of large numbers. When we have larger sample sizes, we would expect that the sample means from the sample are going to be closer to the mean. It's going to reduce that variability within this distribution of sample means. So in that case, the larger the sample size, the less error do we expect from the mean. An extreme way of looking at this, right, is we would expect to have 0 error from the mean if we selected the entire population. So instead of taking a sample of 5 or 10, let's say our population was 100,000. If we sampled the entire population, of course the population mean is going to be equal to the sample we just did, because the sample we just took was equal to the population. So that can show you as the sample size gets larger, the error we expect around the mean or our distribution of sample means is also going to get smaller. So how do we calculate this? So this is probably the one formula that's changing from what we've done before. This is how we calculate it. So if you remember the central limit theorem, the central limit theorem, which is going to be on page 180 for you if you can look at that, basically defines the standard deviation for a population or distribution of sample means to be standard deviation of the population, so this is what we've been dealing with previously, over the square root of n. And this square root is going to have a very interesting function for us. But let's just look at what happens. So if we have a standard deviation of 15, so just like our IQ scores have a standard deviation of 15, we have a sample size of 5. So we've selected 5 people from the population. We've asked for their IQs. The question is, when we select a sample of 5, how far from the mean on average would we expect, or from the population mean would we expect this sample mean to be? So we take the square root of 5, we divide it by, we divide 15, and we end up with 6.708. So that should make sense. Now, what happens as we increase our sample size? Let's take a look. As we increase our sample size, so here we're looking at a sample size of 20, our standard error decreases. Again, this follows the logic. The larger the sample size, the more representative our sample means will be, so the less error we're expecting to find. Additionally, we look at here. Instead, we look at a sample size of 50. Now, because we have a sample size of 50, our standard error is going to be smaller. But notice, as we're going here, the amount of decrease from our original standard deviation of 15, we're not getting as much of a decrease. And that has to do with our square root. As the sample size gets bigger, the effect that the sample will have on reducing the error will also decrease. So here's a graph, and this is also shown to you on page 183 of your book. For a given sample size, or actually I should say, for a given standard deviation, this is the expect. So this is in the population with a standard deviation of 1. As we increase our sample, we'd expect this kind of decrease. Notice really quickly, as we start increasing, going up to about 30, we have a rapid decrease in the amount of error around the mean we'd expect to find, the standard error that our sample means are from. As you go down, notice how it's tapering off. It doesn't have as much of an effect. We have almost 200 here. We're barely even seeing a full tenth of a point decrease in the standard error. Now the book also shows you this based on a different standard deviation. They used a standard deviation of 10, but showing the exact same principle, that as you go out, you're not going to get the same increase, or I should say the same decrease in the standard error. And that should be pretty obvious, that these estimates, when we have a standard, when we have a sample size of 1, are pretty wild. They're pretty far out there. They're not likely to be a good representative of the sample. But as we increase it, we're less likely to experience outliers. We're more likely to be around the mean. There's less great improvement by having larger and larger sample sizes. So while we do expect to see still a decrease in our standard error, it's not going to be nearly as large as we got initially. Another thing, and this is more of looking at the formula, there is actually 2 formulas for our estimated standard error. And here they are. So remember this right here, this is our standard deviation, and this is just our variance. So we can use either to calculate our standard error or standard error event. The only difference here is instead of square rooting just the n, here we're going to square root both variance and n. Because remember, in order to get here, if we wanted to remove this square, take this variance and make it standard deviation, we would find the square root of it. And so we're just doing it all right here. So what formula you use really just depends on what data you have. Now, because we're very interested in standard error, as you can see, the smaller the standard error we have, the less discrepancy around the mean. One question that we may ask ourselves is, what sample size do I need to get a particular standard error? Now, we ask this question a lot of times in research for a couple reasons. A lot of the times, we are funding these projects. We don't want to spend more money on a project than we have to, particularly when we have to go out to grant agencies, and we have to ask, hey, we want to have this grant, we want to do this project, and they're going to ask us, okay, what sample size do you need to find an effect? Now, what we're doing here is kind of a close relative of that. We're not quite there yet. That's something we call like power analysis. But what we're going to do here is we're going to ask ourselves, if we wanted to find an effect, if we have a particular standard error in mind, what sample size do we need to get that standard error? So let's take this example. Now this example, you're going to have examples of this on your homework. We're not going to find this in your book, but this is still important. If the population, so let's take this example, if the population has a standard deviation of 25, how large of a sample is it necessary to have a standard error that is less than 9 points? Now that's an important question. So let's take a look at our formula. So we have this formula here. We have our standard error, so we know our standard error. Well, we know what our standard error we would like to have. We know what our standard deviation is for our population. We just don't know what sample size we need to get that standard error. So it's very simple. Here's our information. This is what we have. Now we just need to solve for n. So just like we were solving for x when we were rearranging the z formula, this is very similar with a few differences. So first thing we need to do, what we need to do is we need to move the square root of n out of the denominator to make it easy for us. So what we do is we multiply that on both sides. That cancels out. So what that leaves us was the square root of n times 9. Now we still want to get that by itself. So what we do is we divide 9 on both sides. And so we get this. We get the square root of n equals 25 divided by 9, which gives us this. And so now we have to ask ourselves, how do we get rid of that? And the answer is, well, what we have to do is we have to remove the square root. So what we do is we square both sides. And when we square both sides, we get rid of the square root, as you can see right here. And this is what we get. So in order to have a standard error of 9, we need to have a sample of 7.7160. Now I'm going to let that sit in. And if this was live, I'd ask you a very simple question. And the question would be, what's wrong with that? And I know right now you're just screaming out what's wrong with it, and I can just hear it. But since you're not here, I'll tell you what it is. The problem with that is that you can't have 7/10 of a person. We have to remember that n, go back in context, n refers to the size of the sample. And importantly, we also have to remember what the question is. The question is, we are looking for a standard error that is less than 9. When we're doing a standard error, we want it to be less than 9 for sure. In this case, we're not worried about it being the reason why we are interested in making sure that it is actually less than 9 is you have to go back to why we're doing it. We're doing this a lot of times. We need to know what sample size we need to successfully run our experiment. And we'd rather err on the side of caution than have a standard error that is much larger than we expected. So in this case, this is one rare instance in which we were always going to want to round up. We're always going to round up. No matter how the sample size works out, even if this was 7.02160 instead of 7.7160, we would always want to round up. We would always round around that up to 8. And the reason for that is, let's take a look. If we do the math, right, so if we used 8, we're going to have a standard error of 8.838. So that is going to be less than 9. It's not exactly 9, but in lieu of chopping somebody into quarters, that's about as close as we're going to get. Now, let's say we decided to round down to the nearest person, right? Which would make sense. In this case, it probably wouldn't make a lot of sense given our rounding rules. But let's just say, for example, it would make sense to round down. We decided to round down. What would that do? What that would give us a standard error. So we do the math here. Standard error that is larger than 9. And if we were trying to figure out what sample size we need to run an experiment, the highest we could ever standard error that we would need is 9, then we would be underestimating. We would need one more individual to run our study. So this is, and I'm going to stress this for you. Please take note of this. This is the one time where the rounding rules don't apply. We're going to round up, always. Even if it's 7.002, we're going to round up. So we want to make sure that we are definitely less than 9. So let's take a second. Let's look at where we're at, where we've been. So I took this from your book. This is on page 185 if you want to look at it. And so we started with an original population of scores. In this case, we're going to look at IQ scores. And this is where we were kind of stuck at in Chapter 6. We just looked at this population. We asked questions. What's the likelihood that we're going to have a population? Or we're going to pull someone with an IQ of 115, or was that person we're going to have an IQ of less than 70? We asked these questions. But what we did here is we said, well, we're not interested in individual scores. What happens if I take a sample of 25 individuals out of that population? So as you can see here, a sample of 25 scores. And that sample is going to kind of range, right? So we're going to have most people falling here towards the mean, because remember that roughly 68% of individuals fall within one standard deviation. And we do have some outliers. We have some people who have low IQs. We have some people that have some high IQs. And if I had to rough it, I believe one standard deviation above the mean would be right about here. One standard deviation below the mean would be roughly right around here. So as you can see, most individuals fall within one standard deviation of the mean, as we would expect. Now, we also see here that our mean is not exactly our population mean. We expect this. This is what we call, remember, our sampling error. This is the natural variation we would expect from the sample. Now, because this is normal distribution, and because it has fairly high, not necessarily 30 points, but it's getting close, we know that the distribution is going to be normal. So as you can see here, this is our distribution of samples. So it has a mean of 100, like we would expect. Remember, the central limit theorem tells us that. Also, notice here that our standard error is smaller than our standard deviation. And this is because we are dealing with a sample of n. So here we're doing n equals 25. Again, sorry for the handwriting. It's kind of hard to write on this. So, we've gone to this point. We have this distribution. Now, because of this is a known distribution, we know that it is a normal distribution. Now we can start talking about probability like we did in the last chapter. We can ask questions about what's the probability of we're going to get a sample that is higher than this, given this particular sample size. So that's what we're going to do. We're going to look at the probability and the distribution of samples. Now, we are going to be changing a couple things going forward than we did in Chapter 6, but I want you to take a second and recognize that what we're doing here is we're just changing very slightly how we're calculating our z-score from Chapter 6. We're adding the standard error into that. But it's essentially the logic of the z-score remains untouched. So I'm going to show you that here. So in Chapter 6, we could ask this question. So what's the probability of randomly selecting a quiz score that is larger than 40? Yeah. Well, let's change that for a second. I actually changed these. We're going to say 35. Just forgot to change this. So ignore 40. We're going to look at what is a quiz score that is larger than 35. So how do we do that? You heard me say. So I've been holding a couple things back from you, of course. So our standard deviation for this particular distribution is 5. Our mu is 30. And what we do is we find a z-score, just like we did in Chapter 6. So let's take a look. So that's the formula. So notice here we're looking at a score minus our population mean over our population standard deviation. And here's our math. So we put 35. This is the x we're interested in. Mu is 30. Our standard deviation is 5. It's a 5 difference. And we have a z-score of 1. And we can go to our unit normal table. So if we want to know the probability, our next step is to go to the unit normal table. So let's take a second here. Let's pop over there. So here's our unit normal table. And again, we want to know what the population of that's likely to having a score that is greater than 35. We know the score is 1. Here's 1. Right here. So the question is, what's the probability? So we can look at the tail, right? So here's our probability tail of 1 point. I can zoom in on this so we can better look at it. So proportion of the tail is 1.1587. So that's the probability. The probability that we are going to get an individual score. Remember, we're looking at individual scores right now. That is greater than 35 is 1.1587 or 15.87% chance we're going to select somebody who has a score of 35 or greater, given our population parameters. So let's take it back here. So now that we've done that, so that's what we've done in the past. So let's look at what we're going to do now. So this is how it's going to change a little bit. So instead of asking the probability of selecting an individual score, we're going to ask what's the probability gain of a quiz score sample mean that is larger than 35. So if we this is important. that has a sample mean of 4. Alright? So this is important. Sample. I'm getting a quiz score sampling. So if I took 4 people from our class and I randomly sampled them, assuming that our mean was 30, what's the probability that I'm going to get a mean of 35? So notice here, instead of an x, we have an m. So we're asking what's the m greater than 35. And here's the 2 changes to our z-score form. The first change is instead of x, we're looking at m, right? So we want to know how far away m is from the mean. So that's one change. The other change is instead of looking at standard deviation, we're looking at standard error. Now remember, standard error is akin to the standard deviation for a distribution of sample means. And so it fulfills the exact same role that standard deviation has. Remember, now we're looking at that distribution of sample means. We're not looking at that raw original population. We're looking at original. Now we're looking at that distribution of sample means. And notice that, though, although that we're changing notation here, we're looking at slightly different things. In the essence, we're asking how far away is this sample mean from our population mean? And how far is that in terms of what we would expect to find in our distribution of sample means? Identical to what we were looking at in concept. We're looking at chapter 6 when we're asking about individual score. So let's take a look at how that's worked. So the first different thing is obviously we're going to have to find our standard error. So we have our standard error. We know that our sample size is 4, because remember it matters what our sample size is. So it goes down here. Our standard deviation is 5. We do a math and we end up with a standard error of 2.5. So we notice that it is lower than our standard deviation as we expect. We expect it to be lower because we expect our sample size of 4 to better approximate. So all we need to do now is look. We've put in our mean here. So our question is, what's the probability of getting a sample mean that is larger than 35? Put 35 in here. And what, in context of how much error we expect on average for our means to fall. So we, again, remember, we expect, just like we talked about in chapter 6, we expect about 68% of our scores to fall within one standard deviation. So we do our math, and here we end up with a higher z-value, which makes sense because this number here is now smaller. We expect less error. So mean differences produce, similar mean differences will now produce larger z-scores. And here's the important thing. How we determine probability does not change. So let's take a second. Let's take a second and look at this. So instead of looking at 1, let's look at a z-score of 2. So here we are. Now we kind of know this from our previous one, but we want to know what's the chance that we are going to get a sample mean. So this is different from what we did in chapter 6, a sample mean that is greater than 35. And we had a z-score of positive 2, so we look at the tail, and we'd have a probability of 0.0228 or a 2.28% likelihood. We are going to select a sample mean that is 35 or higher. So now that we've looked at that unit normal table, we've come to this conclusion. So the probability of getting a z-score that is greater than 2 or greater than 35 is 0.0228. That's the probability. So if you notice that there's this relationship between sample size and, I just ignore that right there. I don't know how we did that. Just the typo. So ignore this. This is 4. So notice that there is this relationship between sample size and z. So let's explore that relationship, because that's going to be important for us to understand. So if we have this relationship, how does it work? So as we increase our sample size, so as n gets larger, our standard error gets smaller. So that makes sense to us, right? So if we holding constant our standard deviation, as we increase our n, we'll make this number smaller. So if n was 5 versus 50, the number we get here is going to be smaller. Now, a smaller standard error is going to lead to a larger z-score, because we should have an n here. This shouldn't be x. This should be n, because we're looking at the same. Sorry about that. What we're looking at here is as this number gets smaller, it's going to make these mean differences that we'd see holding the mean difference the same. It's going to make it less and less likely. So let's look at this more practically speaking. The larger the sample size we get, the more representative that our samples are expected to be from the mean. Because of that, any deviation from the mean is less and less likely. So we end up with a larger z-score. So when we calculate our z-score, we find that the probability we would select that z-score for a given sample size goes down as sample size increases. A couple slides back, when we were talking about how sample size impacts standard error, you can see what effect that has on standard error. So let's take a second and look about where we're at. So first, the question kind of we're asking is, what's the probability of selecting a sample? That's really what we're trying to get at here. What's the probability of selecting a sample? Now, this distribution of sample means that we have here has some particular properties that allow us to look at that. We know, for example, that if the population that it's drawn from is, or if we have a sample size that is greater than 30, the distribution of sample means will be normal, which is perfect for our uses for unit normal table, using our z-test. We also know that our expected value of m, or a distribution of sample means, is going to be equal to our population. Also, we know a little bit about the variability about this distribution. We know that this distribution, when it has the lowest possible sample size, a sample size of 1, it'll be equal to the population standard deviation. And as our sample size increases, it decreases how far we would expect to find those samples from our population. And most importantly, we went and we took, using this distribution, we can discover what the probability is of getting a particular sample size. Now, how we go about it is the notation is a little bit different, but conceptually, remember, it's exactly the same. What we're trying to do is we're trying to look at a mean difference and ask how far away is that mean difference from what we expect to find. So it doesn't matter if we're talking chapter 6 or chapter 7, that concept remains the same. We expect to find, on average, sample means to be within that standard error. So remember, one standard deviation from the mean on either side is about 68%. More than one standard deviation from the mean, so 2 standard deviations, is about 90, right around 97%, 98%, roughly around in there. So that part remains exactly untouched from chapter 6. Now, going forward, what we're interested in is sometimes we're interested in asking, after we select a sample from our sample means. So for the example we gave in chapter 6 of the Netflix, if I give a training to those Netflix employees to reduce their call times, is that new mean that we've got after they reduce their call time. So their mean call time, is that significantly less than what we would expect from our population? So it's a very interesting question. Does our treatment impact the sample so that it differs from the population, what we'd expect to find in the population? And so that's a question. If it does not have an impact, no matter what our treatment will not impact mean scores from our population. Now, remember, we do expect that our samples will not necessarily be exactly on the population. Their means may naturally be a little higher or a little lower than the population. That's when we bring in our standard error. We use our standard error to ask the question, is that mean significantly higher than what we'd expect to find, or really within a range of what we'd expect to find? So, going forward, that's what we're going to be looking at in Chapter 1. We're going to start looking at questions about significance. Now, I do want to mention that, remember, Quiz 2 is going to be on Friday. If you're looking at doing the homework, remember this homework for Chapter 7 isn't due until next Monday. Next Monday and Wednesday, we're going to be lecturing on Chapter 8. And then that Friday, we're going to be taking a quiz over this chapter in Chapter 8. So Chapter 7 will not be on Quiz 2. Now, what I want you to do is I want you to come up with some questions. I'm sure there's probably some things in here over the first glance that may be a little confusing to you. Bring some questions to class. Let's talk about them there. I'll have a handout for us to go over, so we'll practice some of these things in class if you weren't able to follow along. And hopefully we'll have a productive class session tomorrow. All right, I'll see you then. Goodbye.